Thank you, Alison, for this very nice introduction. First, I would like to thank everyone, wherever you are, for logging into our second part of presentation on Introduction to Photodetectors. Again, I'm Slavomir Piatek, and I am, among other things, a science consultant for Hamamatsu Corporation, the sponsor of these webinars. This presentation is divided into basically three parts. In the first part, we'll talk about structure and operation of point detectors, four in particular. Then we'll discuss some applications of photodetectors, focusing on those applications where a given photodetector is a good match. And we'll also discuss an application where a given photodetector is not such a good match. And time permitting, we'll spend some time discussing selection or the process of selection
has joined the meeting
of a photodetector. So let's begin with the structure and operation of photodetectors. The four photodetectors that we'll concentrate on are as shown on the slide. From left to right, PMT or photomultiplier tube, then photodiode, avalanche photodiode, and silicon photomultiplier. So let's look at the basic operation of a PMT. So what you see on this screen is a cartoon version of the PMT structure. It contains three essential parts or components. The photocathode, symbolized with letter K, and then a sequence of diodes, symbolized with letter D. D1, D2 means the first diode, second diode, etc. And finally, one more essential component, P, stands for an anode. Please note that all these components in a PMT must be at some electrical potential, and these potentials are supplied with, in this case, a resistive voltage divider. There is one power supply, and that input voltage, which is on the order of 1,000 or so volts, is divided by a sequence of resistors. So the way a PMT operates is as follows. Light illuminates the photocathode. At the photocathode, a process known as extrinsic photoelectric effect occurs, which means that if light has enough energy, it can allow an electron or electrons to be ejected from the surface of the photocathode. So on the drawing, we have one representative electron emitted from the photocathode. The potentials are set up in such a way that this electron is going to accelerate towards the first diode. As it accelerates, it gains energy, strikes the first diode, and then it embeds itself in the diode and shares its energy with other electrons in the diode. Some number of these electrons will be re-emitted, typically 3, 4, 5 or so, from the first diode. These electrons then in turn will be accelerated towards the second diode, where again they're going to smash into the diode, share energy with other electrons, and ever larger number of electrons will be re-emitted. This process is repeated as many times as we have diodes. Thus, a single electron can turn into thousands, in fact, a million or so electrons by the time they reach the anode. The anode collects these electrons, and the electrons then flow out from the PMT to the outside world. In this depiction, we have a load resistor connected effectively to the ground. And so the conventional current due to these electrons flows into the anode as shown, and it has a value of IP. So in this description, we learned that a single electron or a single photon can result in a million or so electrons at the anode. And so PMT, we would say, has a gain, intrinsic gain. And that gain, as already stated, is very large, again, on the order of million or so. There are two basic designs of PMTs. One common design is known as side-down or opaque, which is shown on the left-hand side of the slide. The light illuminates this point or this portion of the PMT, the grid, and the process of electron multiplication then follows. And we can see that on the right-hand side, this is computer simulation of the paths of electrons that move between the sequence of dinodes. So this is actually a realistic depiction of the PMT. Now, another common design is known as head-down PMT. Again, a portrait of such PMTs is on left-hand side, and on right-hand side, again, we have a computer simulation of the paths of electrons in this particular type of a PMT. It is very convenient to represent operation of any photodetector using equivalent electrical circuit. And so what you see on left-hand side is such circuit for a PMT. So it consists of a current source, which produces a current given by the equation below, where P sub 0 is the incident light power, S sub K is known as cathode spectral sensitivity, and mu represents the intrinsic gain of the device. Sometimes in case of a PMT, we can combine S sub K and mu and call that anode spectral sensitivity. So in addition to the current source, we have a capacitance. We can call this capacitance a terminal capacitance, and it will be primarily a capacitance between the anode and the last dynode. It's worth noting that for PMT, this capacitance does not scale with the size of the active area. This is unique and certainly unlike what we see in case of PN junction devices, to be discussed a little bit later. In addition, we have a resistor between the anode and effectively the ground. This is not the load resistor. This is a resistor that is intrinsic to the PMT. And that resistance is very, very, very high. 10 to 8 and more, actually more likely more than 10 to 8. And so therefore we have an anode and the ground. And if I were to connect the anode and the ground with a short, then the current here in this short would be equal to the current generated by light. There are basically two ways of operating a PMT. One way, which is depicted in both circuits, is known as anode grounded operation. So in this scheme, the cathode is at the very high negative potential, and the potential then increases as we move towards the anode, and anode is effectively at the ground. In this case, not exactly at the ground because of this load resistor, but hopefully close to it. So again, the current, conventional current flows into the anode, and so therefore we would have some negative potential at this point using Ohm's law, and at the load resistor, and that voltage then would be amplified by, say, voltage amplifier to give us some output voltage. Now, this scheme here uses so-called resistive loading, and the advantage of that is that it's a very straightforward and inexpensive way of converting current to a voltage. However, one disadvantage of this approach is that if this resistor is quote unquote too high, then this potential here at the anode deviates from zero, perhaps substantially, which will then affect collection efficiency in the PMT, which will eventually lead to a nonlinear behavior. One can improve on this by utilizing a transimpedance amplifier shown on the right-hand side. The great advantage of this circuit is that this potential here is effectively at zero. We call this a virtual ground. However, the voltage V sub zero is still equal to the current that flows into the anode times the feedback resistor RF. One should note, however, that this circuit is rather more complex, needs its own power supply, and is certainly more expensive compared to a resistive load. Another scheme of using a PMT is known as the cathode grounded operation. In this case, the cathode is, as the name indicates, at the ground. This operation is commonly used in scintillation, where for the to reduce the amount of noise, indeed, it's advantageous to ground the cathode. Therefore, in this operation, the anode has to be at the highest positive potential. Therefore, to employ detection electronics, it is important to have so-called coupling capacitor in this circuit C4, which separates the very high potential at the anode from the electronics. Please note that this scheme or this cathode grounded operation can only be used for pulse or AC input light. One should not use it for DC. So with that, we are going to now turn our attention to devices that have a PN junction. So these devices are photodiode, linear mode, avalanche photodiode, and then silicon photomultiplier. What you see on this slide is a current voltage characteristic for a PN junction. There is no light. So this curve is effectively a dark current as a function of voltage. So the three devices that I've mentioned before will be operated in three distinct regions. And so photodiode will be operated close to the origin, which means that the reverse voltage that we're going to apply to the photodiode is going to be small or smallest out of the three devices, typically anywhere from 0 to 10 volts reverse or so. Now, please note that as I increase the reverse voltage, eventually this curve, dark current curve, starts to increase more rapidly than for lower voltages. And so around this knee is where a linear mode avalanche photodiode operates. If you're wondering why this curve why this current begins to increase, the answer is that there is a gain mechanism in the APD. That gain mechanism we'll discuss shortly is based on impact ionization. There is a voltage known as a breakdown voltage, which separates this linear mode operation from the what we call Geiger mode operation. The significance of this voltage is that if the reverse voltage is higher than VBD, then the avalanche, if I produce an avalanche in the device, that avalanche by itself would not quench, would not stop. It has to be stopped either passively using, as we'll discuss later, a resistor, or actively using a current sensing circuitry and a MOSFET transistor. So speaking about gain, let's just reiterate what we just discussed on the previous slide. So now I'm going to shine light. So shining light causes this IV characteristic to effectively shift down by the amount that will be proportional to the incident power of light. In case of a photodiode, a single photon can produce a single electron-hole pair uh, in a region known as depletion region. Please note that these depictions of the depletion region or the p-n structure are not to scale. So it's highly exaggerated size of the depletion region. In the depletion region, there is electric field which separates these two charge carriers. Therefore, the electron drifts towards the n region and the hole drifts towards the p region. And you can think of electron then recombining with the hole, producing a photocurrent. In case of APD, the electric field here is sufficiently strong, and so that if I produce a single electron hole pair, these carriers will accelerate and can ionize additional silicon atoms. In case of a linear mode APD, the useful gain is up to about 100 or so. In case of SPAD, which stands for single photon avalanche diode, the electric field is so strong that a single photon effectively would create infinite number of pairs. This process of impact ionization just continues, provided that we maintain the bias voltage across. In practice, this is not very useful, and it will be advantageous to quench that avalanche, stop it, and bring back the structure to light-sensitive state. So let's say a few things about photodiode. This would be a typical structure cross-section of the photodiode. Light comes from the left. There will be some window. It's often a filter. The lights typically approaches on the P side. Here, the gray area shows the depletion region. It is advantageous again for the creation of electron hole pair to occur in the depletion region or close to it. Then we have N, and then N plus, and the cathode. This N plus layer is known as the ohmic contact. So let's again look at the cartoon version at the operation, basic operation of the photodiode. Again, gray represents depletion region. Please note that there is a built-in electric field. The depiction here is known as the short circuit operation. A photon comes in from the left, creates electron hole pair. These get separated by the electric field. They drift hole to the p region, electron to the n region, and then you can think of electron as going through the wire and recombining with the hole. That produces a photocurrent I, as shown. Just like in case of a PMT, there is an equivalent circuit that one can utilize to understand the behavior of a photodiode. And so all the components, electrical components that you see in this rectangular blue region are the components depicting a photodiode. Thus, we have a current source, IPH, where the current is given by sigma times P, where sigma stands for spectral sensitivity of the photodiode, and P for incident power. D here represents the ideal diode described by Shockley equation. This is a shunt resistance, which represents resistance of the depletion region. It's larger it is, better it is. However, it does depend on the bias voltage and depends also on temperature. C sub J represents the junction capacitance. That's the capacitance of the depletion region. And R sub S represents the resistance, combined resistance of the undepleted part of the photodiode. Now, V sub B here represents the external bias. Incidentally, this would be the anode. So this is a reverse bias circuit. And RL represents the load resistance. So let's quickly review some basic modes of operation of a photodiode. All these modes are utilized in real life. Um, so first, maybe let's discuss the photodiode equation. And so I here represents the total current flowing through the photodiode. And it's effectively given by this part, which is the Shockley equation describing ideal diode, and then minus IPH. This represents the photocurrent given by sigma times P. So this is a photodiode equation. Now, what we observe depends where our observation or where our Q point is. So let's start with so-called open circuit operation. In this operation, there is no bias applied to the photodiode. There is no current flowing. And so what one observes is the voltage. So if I were to change the light level, these different light levels are depicted by different values of phi, then the voltage at the terminals of the photodiode would depend on the light level in the way given by this equation. So one can see that the open circuit voltage would depend logarithmically effectively on the incident light power. One advantage of this mode is very high dynamic range. Now, in another operation known as the short circuit operation, the Q point is on the I-axis. In this case, the anode and the cathode are simply shorted, and there's no voltage, therefore, and so one would observe a short circuit current, which is approximately, a good approximation, equal to the photocurrent. Okay, another very common mode of operation is depicted here with this Q point. So we apply the reverse bias, and we also have a load resistor from which we are going to take the signal. To find the Q point, we would draw a load line for this circuit. The load line is shown by this black line with one end at the VB, which is the bias voltage on the V-axis, and the other point is VB over R on the I-axis. The intersection of the load line and the given characteristic gives me the Q point. Please note that as the light level changes, that Q point would move along this line depending on the light level. Since we're in the flat part of the IV characteristic, we have good linearity. Now you may be wondering, why do we use this reverse bias? And the reason, well, among other, is that the capacitance, the junction capacitance, is a function of reverse voltage. And by biasing the photodiode, we reduce the capacitance, which means that this mode would be more popular in applications where speed or frequency response is important. And yet in the final depiction, we don't have any load resistor. We just reverse bias the photodiode. And so here the load line is simply the vertical line, and the Q point would just move up and down depending with the light level for this mode of operation. So in the next few slides, I would like to show you practical circuits that one can use for these various modes of operation. So in case of open circuit, I would use this voltage follower. This is the operational amplifier. The one advantage is that there is a very high input impedance, allowing us to measure the voltage of the photodiode without loading unnecessarily the device. And as noted here, open circuit configuration is very useful, often used in absorbance measurements. Now here is a short circuit that one can use for short circuit operation. Again, we use a transimpedance amplifier with a feedback resistor, but please note that both terminals here, plus and minus, are at ground, and so therefore effectively the photodiode is shorted. However, we can convert current to voltage using this feedback resistance. Now, this circuit corresponds actually to, sorry to go back to this mode where we do not have, where we bias the photodiode but have effectively no load resistance, because again, we're using transimpedance amplifier. So this point is at a virtual ground. But again, we can convert current to voltage because of the feedback resistor. And this is one of the more popular configurations of using the photodiode. And this one is a circuit where we use a load resistor, and we take the signal from the load resistor. The purpose of this capacitor is to separate the DC part from AC. So in this particular case, I'm interested not in DC component of light, but in its fluctuations. So let's now turn our attention to avalanche photodiode. So what you see here is, again, not to scale artist conception of the basic structure of this device. Again, some of these regions are highly exaggerated. So light comes from the left. We have several layers of a semiconductor. The important layer is the avalanche region. That's where the actual impact ionization occurs. At the top, we have the profile of the electric field. Please note that electric field is not zero here in this region, but smaller than in the avalanche region. So it is advantageous that when light comes in, it creates electron-hole pair, not in the avalanche region, but outside of it, either on left-hand side as shown here, or on right-hand side, not shown. So we create the electron-hole pair. The electric field here in this region separates the two carriers, and one of them is going to drift towards the avalanche region. It injects itself into avalanche region and produces or initiates avalanche. You might be wondering, why do we do that? Why not just create the electron-hole pairs in the avalanche region directly? And the answer, short answer to this question is that you would have much higher noise. So it's for the purpose of lower noise that we would prefer that only a carrier of a given sign, either electron or hole, inject itself from the same boundary into the avalanche region. So here you see a basic, by the way, the circuits that we discussed for photodiodes can be also used for avalanche photodiode. In fact, the equivalent circuit, electrical circuit, is exactly the same, with only one difference, that the current source has a gain component in it. So just a few points about the operation of APD. And so APD is going to be biased below the breakdown voltage. It has a gain, and so therefore a single photon can lead up to 100 electron hole pairs or so. The avalanche is self-quenching, so you do not need any external circuitry or quenching resistors to terminate the avalanche. Now here, the avalanche or the gain comes with noise, which is expressed by a noise factor, F, which in case of APD is approximately given to gain raised to a power x, where x is about 0.3 to about 0.4. So we see that the excess noise for APD actually increases with the gain. And this is why Even though you could actually have a gain of 1000, that gain would come with very high noise. So that's why I keep saying that the useful gain is up to about 100 or so, where the noise is still manageable. I should have said earlier that in case of a PMT, the excess noise uh, actually diminishes with the gain. So there's the opposite behavior, and it's approximately given by the gain of the first dynode divided by that gain minus one, approximately. So another important point about the gain of a APD is that it actually has quite sensitive behavior when it comes to temperature. And so looking on the right-hand side of this slide, we see the gain as a function of reverse voltage. And so please note that for a given reverse voltage, if I change temperature, the gain changes quite appreciably. Therefore, that change in gain, of course, with temperature uh, is going to lead to increased noise, um, especially if you don't know that temperature changes, then the output is going to simply vary with temperature. And so to prevent that, one can do two things: either stabilize the temperature or use a circuitry known as temperature compensation circuitry, which will keep the gain fixed even though temperature changes. Also, what this plot shows are the two regions of operation. So there's a linear region, and then we transition into the Geiger region. Please note, however, that the avalanche photodiode built or structured for linear operation should not be used in the Geiger mode and vice versa. So let us now transition and discuss silicon photomultiplier. On the left-hand side, you see a top view of this device. It consists of microcells, uh, and each microcell is a series combination of APD operating in Geiger mode and a quench resistor, a resistor necessary to quench the avalanche that arises in a single microcell. But first, some details about the sizes. The size of a microcell, and you see here a top view of a single microcell, will range from 10 by 10 microns to about 100 by 100, depending on the design. And the active area will range from about 1 by 1 millimeter to 6 by 6. These are the currently available ranges for these sizes. The number of microcells will be from several hundreds to tens of thousands. So looking at the middle of the slide, again, we see a top view of a microcell. This wiggly structure here is the quench resistor. And this surface is the oxide that separates the quench resistor from the APD structure below. The quench resistor and the APD structure are connected together. I guess this will be the contact. So let's now look at this electrical circuit representing SIPM. So a single microcell, again, is APD in operating in Geiger mode, connected in series with quench resistor. But please note that all microcells are connected in parallel. Therefore, this device has only two prongs, the cathode and anode. Here it is how it operates. Suppose I have two photons that arrive at the active area at two different times. And so the first photon creates a current pulse in this microcell. That current pulse then propagates or moves through the load resistor, producing a voltage pulse. The second photon struck at later time. And so therefore we have a pulse corresponding to that photon at later time. So one could say that the output from SIPM is a chronological superposition of pulses, current pulses or voltage pulses that the device produces. Please note that for this device to operate, the bias voltage has to be greater than the breakdown voltage. That difference between the bias voltage and breakdown voltage is known as overvoltage, which is typically 3 or so, 3, 4, 5 volts for the device. The overvoltage is probably the most important parameter which affects almost all aspects of the operation. And typically it should not be varied. The manufacturer is going to recommend a given overvoltage for the device. So now let's look at a pulse resulting from a single microcell. If we have enough bandwidth or detection bandwidth, we can see this fast component rapidly rising a pulse, then a decline, and then a slow component. If we don't have enough bandwidth, we may not be able to see the fast component. The quenching of the avalanche occurs somewhere here, and then the microcell goes into what we call recovery state, which is depicted by the slow component. The recovery time is approximately equal to 5 times the RC time constant, where R is the value of the quench resistor and C is the value of the junction capacitance of a given microcell. These recovery times can vary from tens to hundreds of nanoseconds. But as noted in practical situations, this recovery time is also a function of detection bandwidth, which is a function of the circuitry, front-end electronics used in conjunction to the device. I would like to discuss briefly a phenomenon that occurs in this device known as crosstalk. And the reason for this is that it contributes to excess noise, to be discussed shortly. So on left-hand side, we see a discharge, an avalanche in a microcell. However, this discharge, this avalanche produces photons, and some of these photons have enough energy to initiate discharge or discharges in neighboring microcells. So one event now can cause almost other events at almost the same time. And so instead of getting one PE waveform, one sees superposition of such waveforms, in this case, 2, so we get 2 PE event, which would be attributed to the crosstalk. If I had 2 additional discharges, then we would have a 3 PE waveform or so. Please note that this primary discharge can be caused by a photon, but could also be caused by a dark event. So, here again is our SIPM, which is biased, and we're observing the signal from it. Again, like a PMT, this device has intrinsic gain, and one can show that that gain, mu, amazingly in my view, is given by overvoltage times junction capacitance divided by the quench resistor. If you're wondering why did I say amazingly, it's because it does not depend on the value of the quench resistor, but depends on the amount of overvoltage and the value of the junction capacitance. Now, so this equation shows that the gain depends linearly with overvoltage. However, typically, again, one is discouraged from changing the gain because that overvoltage affects other aspects of the device, like photon detection efficiency, probability of crosstalk, and others. And so, as stated before, every gain, intrinsic gain, comes with noise penalty. And so in case of this device, excess noise is approximately equal to 1 plus probability of crosstalk, which for modern devices is typically less than 10%. Now, this slide reminds us why intrinsic gain is advantageous. We have two situations where photodetector in the top panel has intrinsic gain mu, and in the bottom panel it does not. So gain here is 1, but we have a voltage to voltage amplifier with gain mu. Without going into details, just a brief statement is that the detection signal to noise ratio for the top situation would be higher than for the bottom one. So these are not equivalent circuits. Intrinsic gain of the photodetector will ultimately improve final signal to noise ratio versus a situation where we try to have a voltage amplifier with the same gain. Not the same. Now, this statement can be made more concrete with a little bit of math. We talked in the first part of this presentation about signal to noise ratio of the detection. So at the top we have a signal, at the bottom we have a combination of noises. Mu is the gain. So I can divide numerator and denominator by the gain. And so if the gain is very large, this term here can be made negligible. But this term represents noise of the effectively of the front end electronics, which in this equation would be a resistor, but in some sense it doesn't matter. And so the intrinsic gain suppresses the noise of the front end electronics, ultimately improving the overall detection signal to noise ratio. Silicon photomultiplier can be used in NPMT as well, and APD to some extent can be used in a photon counting mode. However, can also be used in analog mode. In the photon counting, the pulses are separated in time, so we can simply count them, and this is not so difficult as it sounds. However, if the light intensity increases, the pulses begin to overlap, so we can't count them anymore. However, it is still okay to use analog detection where we would measure some average output current or voltage. And this is underscored with this slide here. So the photon counting mode, analog mode, where we measure against some average value of resulting current or voltage. Let's spend some time discussing photon counting. This would be a typical setup. We have a photodetector and then a sequence of amplifiers. The important component is discriminator, which is going to discriminate pulses based, for example, on their amplitude. If a pulse is too high above the upper level discrimination, it will be rejected. If it's too small, below the lower level, it will be rejected as well. The pulses that do make this cut then go into pulse shaper, which then issues a standard pulse, which is then counted by the counter. Photon counting, if it's possible, is advantageous because the output is less susceptible to gain variations. Because again, if the gain varies a little bit, maybe up or down, the amplitude changes up or down. But as long as you are within the band, this pulse is going to be counted. However, in analog operation, gain variations are going to lead to immediately to the changes in the measured values of current or voltage. Here is the equation for signal to noise ratio in the photon counting approach. And please note that the signal to noise ratio depends a square root of a measurement time. And so if possible, I can improve signal to noise ratio by increasing the sampling time. This may not always be possible, but if it is, that's one great advantage. So let's now quickly go through some applications of the above photodetectors. And for each photodetector, I'm going to list or name an application that is for which that photodetector is a good choice, and then another one which for which it is not made perhaps um, the optimal choice or the best choice or even good choice. So let's start with the PMT and bioluminescence. Here, the purpose is to determine the presence of some compound in some compound. So the way we do it, we have a solution, say with that compound, we are going to add additional compound which binds to the molecules that we are looking for, and as a result is going to stimulate luminescence. And that luminescence will be then observed by the photodetector. However, the luminescence typically is very weak and the light is diffuse, which cannot be focused. And so PMT is a good choice because its large active area can increase the amount of light that we detect, and the intrinsic gain allows us to see weak signals. Now, an application where PMT would not be ideal is automotive LiDAR. LiDAR is a technique of finding distance using light. In this depiction, this is a time of flight approach where a light source produces pulse of light, which reflects from the target and is detected by the detector. We measure time of flight, and from that, we get distance. However, if this is meant to be on cars, PMT is not ideal because it's mechanically fragile, has a limited dynamic range, and if accidentally exposed to full light while powered, it can be permanently damaged. However, please note the asterisk here, there are PMTs that are ruggedized that can be even used in oil logging, but these are special types and special types of PMTs. Let's now look at photodiode. One common application of photodiode is absorbance measurement, where we would like to know the concentration of some substance. So we illuminate the substance with light whose intensity we can control, and the amount of light that is diminished will be proportional to the concentration of the substance under investigation. And so photodiodes are very good because of low cost, very high dynamic range, very suitable. However, one would not use probably photodiode if one were to look for dark matter. Dark matter is this hypothetical substance that dominates the composition of the universe. In one setup, the presumed dark matter particle is going to interact with the scintillator, which is a liquid xenon at very low temperature. And as a result of the scintillation, we produce electron here. And that electron accelerates and produces light from ionized xenon gas. That light is emitted in all directions and has to be captured by photodetectors. However, the amount of light is small. It's a pulse, also of short duration. And photodiodes do not have intrinsic gain. And also here it's advantageous to have large active area, but in case of the photodiode, if active area is large, we also have large capacitance. And so typically in this application, it is actually PMT that will be used for these detectors. Now let's look at APD, avalanche photodiode. Here's application where it is a good choice. Here, this is a regenerator. We have an optical fiber in which a light signal propagates, but it's weak. So the APD detects that the light signal, converts it to electrical signal, which then uh, is fed to a laser diode, which then regenerates the signal with the correct time properties, but stronger in light level. So the high dynamic range, high intrinsic gain, very wide bandwidth make APD a good choice for this application. We've mentioned oil logging before. APD would not be a good choice because its gain is highly sensitive to temperature, and the temperature here can be quite high. After all, it's oil logging. Drills are drilling into a rock. And finally, let's turn our attention to silicon photomultiplier. An application where it is extremely well suited is PET, positron emission tomography, where we can image functions actually in organs like brain in this case. It is advantageous to have photodetectors that have small active area and have high sensitivity to blue light, and also um, have high intrinsic gain. And so silicon photomultiplier fits all these requirements and effectively replaced a PMT that used to be used in this application. And finally, we talked about LiDAR, but there's another type of LiDAR called survey LiDAR, where we use infrared radiation typically to, for example, determine the topography of the underlying surface. Since silicon photomultipliers do not have sensitivity in IR yet, um, these would not be well suited for this application. Finally, let's spend some time discussing the process of selection of a photodetector. Time is short, therefore I'll try to just quite briefly mention the main points. So here at Hamamatsu, we like to talk about the widths process approach, where each letter represents a parameter that one needs to consider in the selection. So W stands for the wavelength of light, I, the intensity or amount of incident light power, T for temporal characteristic of light, whether it's DC, AC, or a pulse, S, spatial characteristic, whether light is diffuse or collimated or something in between. And finally, the dollar sign represents the price. So again, every light has certain spectral composition. Could be black body to emission, like shown here, where you have distinct wavelength components in the light. Typically, very often, a given application will deal with nearly monochromatic light. Light intensity, again, we talked about how much light we have, say, passing per unit area, per unit time. These are the temporal characteristics, DC, AC, pulse, and again, spatial, collimated, and diffuse. So probably the first two, the wavelength intensity, are the most crucial parameters. So selection based on wavelength. If my science light, for example, has a wavelength of 900 nanometers, currently this is a plot of photosensitivity as a function of wavelength. So currently, the photodiode S1087 would not work because it has no sensitivity at 900. So the first choice is to choose a photodetector or consider photodetector that has non-zero response to a given wavelength of the science light. typically one would want to have actually the maximum response. In this particular case, it would be for 900, it would be this device S1087. So please note that such plots, response, photosensitivity as a function of wavelength are provided for all devices by manufacturers. So on the right-hand side, we see such plot for certain PMT. Okay, then we have a selection based on intensity. There are a number of bullet points here. We don't have much time to go over them in any great detail, but I will summarize in a single sentence. Here we have to optimize or maximize the signal to noise ratio. So ultimately, we want signal to noise ratio to be greater than 1. So if one can estimate the incident light power, one can then consider signal to noise ratio that will be given or will be yielded by the various photodetectors under consideration. Now, that you may be wondering, well, will there be a difference? And the answer is yes, because remember, different photodetectors have different amounts of dark current, have different intrinsic gain. So for a given load, electronics or front-end electronics, the overall signal to noise ratio is expected to be different. So the main criterion is that S over N must be greater than 1, and ultimately one would like to have it as large as possible. Sometimes estimating signal to noise, sometimes estimating incident light power is difficult. I know of such situations myself from personal experience. Therefore, another approach is a trial and error. One can simply try different photodetectors and empirically determine which one gives the best performance from this point of view. Another important point to make is that signal to noise ratio will depend on bandwidth, detection bandwidth. And so it is crucial that the user uses only the amount of bandwidth that is necessary for that particular detection. Too much bandwidth will only add noise to the detection, and too small bandwidth may diminish the fidelity and the size of the signal. So one has to be careful about this particular parameter. So if I were to compare the four photodetectors from the point of view of intensity, I could make this rough plot that you see on this slide. If I am at the very, very low light level, PMT is probably the best, well, not probably, it is the best choice. And by low light level, I mean singular photons striking the active area per second. However, if the incident irradiance increases, then silicon photomultiplier now becomes a possible choice as well. Increasing irradiance even more, then APD becomes a third possible choice. Like in this region, for these irradiances, right now I would have a choice perhaps between SIPM, APD, and PMT. And what choice I ultimately make will depend perhaps on other considerations. If the light level is sufficiently high, even though there may be multiple choices, one typically will go with the photodiodes. If you have plenty of light, photodiode is an excellent choice. Now, what about if frequency is important or temporal behavior? In this case, one has to watch for terminal capacitance, since that terminal capacitance will affect the bandwidth of the detection. For PN junction devices, terminal capacitance is a function of reverse voltage, but also a function of active area. So there we have compromise when it comes to active area between the, the signal uh, um, amount of signal, right? Because smaller active area captures less light versus larger active area, and the bandwidth. So there's a trade-off between the two. Now, selection based on spatial characteristics. Again, the bottom line is that you cannot uh, focus diffuse light, and so there capturing more light will mean you have to have larger active area. If the light is collimated, yes, you can focus. Then one can use lenses then to effectively increase intensity. Please note that when you use a silicon photomultiplier, one should not focus light to a spot on the SIPM because you're going to limit its dynamic range. So after the lens, one should then use diffuser to diffuse the light impinging on the device. Finally, if you consider all these considerations and you still have a choice between PMT, SIPM, APD, and photodiode, maybe the price can break the tie. This is, by the way, unlikely, but suppose that you've reached this point. So for standalone devices, the pricing would be such that PMT will be the most expensive and photodiode the least expensive. But these are for standalone photodetectors. Please note that photodetectors must have biasing circuits and detection circuits. And so a better way to look at pricing is not for individual components, photodetectors, but for the entire systems. Now, apart from these considerations, there are other considerations one can consider, and these might be even more important than the previous ones, like temperature stability, magnetic immunity, radiation immunity, power consumption, ruggedness, size, dynamic range, time jitter, and environmental considerations. So there are many factors. This is why it's nearly impossible to create some sort of flow chart, easy flow chart, where one can simply select the photodetector following the basic questions. It's rather can be complex process, and so if the user is not sure or confused, the user is strongly urged to contact the manufacturer to help with the selection. In our case, the Hamamatsu Corporation. I would like to thank everyone for listening to this webinar, and I encourage you to contact our company, or if you have any specific question to me, the contact information is at the bottom of this slide. I would like to also make you aware of upcoming presentations, additional webinars with the calendar on this slide. Again, thank you very much and goodbye.